Lesson 6, Liquid Penetrant Testing. Introduction to Liquid Penetrant Testing. Liquid penetrant testing, abbreviated PT, is an NDT method used to locate discontinuities which are open to the surface in a variety of different materials. In simple terms, PT is accomplished by processing a part through a series of steps to apply a colored or fluorescent dye on the surface of the part and to wait for the liquid to be drawn into discontinuities. When ready, the surface penetrant is removed. Penetrant that is trapped inside discontinuities remain and is visually apparent, which would otherwise be invisible to the naked eye. Historically, penetrant testing evolved from the railroad industry's oil and whiting method used in the late 1800s through the mid-1900s. An oil and kerosene mixture was applied to rail car wheels, the surface was cleaned of excess oil, and then coated with a white chalk mixture. Upon drying, the wheel was struck by a hammer to vibrate and migrate the oil from the discontinuities to be visible in the white chalk coating. Making discontinuities more visually apparent is the basis of the PT method. PT not only makes the discontinuity indications appear larger, but it also provides a means to improve the contrast between the discontinuity and the part's surface with the use of color or fluorescence and a neutral background, typically white. Making discontinuities appear larger on a contrasting background greatly enhances their presence and visibility to overcome the limited visual acuity and contrast sensitivity of the human eye. Advantages of liquid penetrant testing. Complete and quick inspection coverage, regardless of part geometry. Variable sensitivities to choose from for test optimization. Highly sensitive in detecting small, tight surface discontinuities. Can be used on a variety of materials, including ferrous and non-ferrous metals and some nonmetals. Rapid and cost-efficient processing of large volumes of parts. Immediate inspection results with discontinuities visible directly on the part's surface. Approximate discontinuity size, shape, and location is visually presented. Versatility of equipment, including stationary, portable, and automation. Low equipment and operating costs. Requires minimal classroom training. Limitations of liquid penetrant testing. It does not reveal subsurface discontinuities. Discontinuities must be open to the surface. The test surface requires a clean, bare surface. Pre-cleaning is required and is incredibly important. Surface finish and roughness can affect inspection sensitivity. It does not work effectively on porous materials. It is not useful after mechanical operations impact the surface condition of a part. Multiple process operations and controls to maintain peak performance. Post-cleaning of acceptable parts or materials is required. Discontinuity depth cannot be assessed. Principles, properties, and mechanisms. Chemists, engineers, and manufacturers have collectively formulated PT chemicals to make the method fairly simple for NDT professionals, assuming established procedures are followed and process controls are in place. The ability of a liquid to cover the surface of a part and enter any surface opening regardless of orientation depends primarily on surface tension, wettability, and capillary action. Properties that impact the relationship between wettability and capillary action. Very poor wetting ability. Penetrant will not draw into discontinuities, not desirable for PT. If a drop of our penetrant material is placed on a piece of glass and the angle of the molecule is greater than 90 degrees, we have very poor wetting ability. If we were to put a beaker into a bath of the penetrant material with a very poor wetting ability, we would have a capillary depression which inhibits penetrant from being drawn into discontinuities. So we don't want to use a penetrant that has very poor wetting ability because it will not be drawn into any discontinuities. Poor wetting ability is defined as if we put a drop of our penetrant on glass and the angle from the edge of that drop was equal to 90 degrees, that would give us poor wetting ability. If we were to put a tube into a bath of the penetrant, we would have no capillary rise or depression, and it inhibits the penetrant from being drawn into discontinuities. What is desirable for liquid penetrant testing are penetrants that have a good wetting ability. And that's defined as if we were to put a drop of penetrant on a piece of glass, the angle would be less than 90 degrees. That would be an indication of good wetting ability. If we were to put a beaker into a bath of this penetrant, we would have a capillary rise, showing that we would be able to have the enabled penetrant to be drawn into discontinuities. Now, as a liquid penetrant testing technician, you don't have to formulate your penetrants. You purchase them and they always come with good wetting ability. But we want to make sure that we're using penetrants that are designed for penetrant testing. If we were to use an oil that wasn't designed for penetrant testing, it may have very poor wetting ability or poor wetting ability. And we want to make sure that we have a good wetting ability for our penetrant oil. Surface tension. The surface of a liquid tends to act as an elastic membrane due to the liquid's cohesive force, holding the liquid's surface molecules together. Cohesive force, or surface tension, is the reason a small amount of liquid can take the shape of a sphere or a droplet. It is also the same reason some lightweight insects can literally walk across water. The cohesive forces creating the surface tension can be very strong. However, for PT liquids, the liquid's adhesive forces must be stronger than its cohesive forces to properly wet the surface and be drawn into discontinuities. Adhesive forces enable the liquid to adhere to another substance it is in contact with. These cohesive and adhesive forces are important in what is known as wetting ability. Wetting ability, or wetting action. Wetting ability refers to the ability of a liquid to spontaneously spread and adhere to solid surfaces. When a liquid comes into contact with a solid surface, the cohesive force responsible for surface tension competes with or is countered by the adhesive force between the liquid molecules and the solid surface. To freely and thoroughly wet the part surface, the liquid penetrant's adhesive forces must be stronger than its cohesive forces. These forces determine the contact angle the liquid forms with the surface. The contact angle. The contact angle is the measured angle the liquid makes with a solid surface. If the contact angle is less than 90 degrees, the liquid will wet and spread, and we consider that good wetting ability. If the contact angle is 90 degrees or more, the liquid will not wet the surface and will remain as a rounded drop. Liquids that bead up on the surface of a test object do not have good wetting ability, are difficult to draw into a discontinuity opening, and are generally undesirable for PT. Capillary action. Capillary action is defined as the tendency of a liquid to penetrate or migrate, seep or climb into small surface openings such as cracks, pits, or fissures. When a tube with a small inside diameter is inserted into a liquid, the liquid level inside the tubing may rise above, remain even with, or be lower than the outside liquid level. If the contact angle between the liquid and the tubing wall is less than 90 degrees, the liquid will be higher in the tube than on the outside. When the contact angle is 90 degrees or greater, high surface tension is apparent, providing poor wetting ability. The liquid will not rise above the outside level and may even be depressed. Liquid penetrant processing. Although liquid penetrant testing is a fairly simplistic NDT method, its success in finding discontinuities is contingent upon following a fairly explicit process or sequence of operations. This process is defined by the method of penetrant removal. There are 4 methods of penetrant removal which are based on the composition of the penetrating oil. Method A, Method B, Method C, and Method D. Method A is considered water washable. Liquid penetrants containing an emulsifying agent or detergent so as to be able to be washed from the part's surface with a water spray rinse. Method B, post-emulsifiable lipophilic. These describe liquid penetrants that do not contain the emulsifying agent and cannot be removed with plain water. Removal is made possible by applying an oil-based emulsifier to dwell just prior to rinsing with a water spray. Post-emulsifiable liquid penetrants are formulated to optimize their penetrating and visibility characteristics. Method C, solvent removable. Solvent removable penetrants require the use of a solvent to remove the penetrant from the part. Any oil-based liquid penetrants can be removed with solvents. This method is usually used for portable field liquid penetrant inspections using aerosol cans. Method D, post-emulsifiable hydrophilic. This method uses liquid penetrants without an emulsifier. Hydrophilic removal is accomplished with a water-based solution and a detergent, soapy surface action. The hydrophilic method is preferred over the lipophilic method, as it provides greater control over the removal process and produces less residual background. There are 7 basic processing steps for liquid penetrant testing. 1. Part surface preparation. 2. Apply liquid penetrant and dwell time. 3. Remove excess liquid penetrant after the dwell time. 4. Apply a developer and any drying if needed. 5. Indication development dwell time. 6. Inspection and documentation of indications. And 7. Post-cleaning. Step 1. Part surface preparation. Regardless of the PT technique used, this initial step is probably the most critical. The surface of the part must be clean and dry, free of any contaminants including oil, grease, or dirt that could prevent the penetrant from being drawn into the discontinuities. If the surface appears to have been sanded, grit blasted, or machined, the part may also require acid etching, if allowed, to reopen the discontinuity cavity that may have been smeared over from the mechanical processes. Step 2. Apply liquid penetrant and dwell. After the part surface has been cleaned and dried, liquid penetrant is applied by spraying, brushing, or immersing the part in a penetrant bath. A wait time, called a dwell time, after applying the penetrant is required to allow the liquid penetrant to sufficiently be drawn into a discontinuity cavity. Dwell times vary, which are typically 10 to 30 minutes, but depend on the application, penetrant materials, test object surface condition, geometry, and expected discontinuity types and size. Dwell times may exceed the recommended time if permitted, as long as the penetrant does not dry on the surface. Step 3. Remove excess surface liquid penetrant. This step requires careful control over the excess surface penetrant removal process while simultaneously ensuring the penetrant that has been drawn into discontinuities remain there. Depending on the penetrant technique selected, excess surface penetrant can be removed using a solvent, spray rinsing with water, or an emulsion/spray water rinse combination. If fluorescent penetrants are used, an ultraviolet A lamp will help to determine when the excess surface penetrant has been removed. Step 4. Apply developer and drying. Developer is applied to the part to give a thin white surface coating to wick the trapped penetrant from discontinuities and give a uniform white background color to provide contrast with the discontinuity indication color. Drying of the part is required before application of developer unless an aqueous developer is used. Aqueous developer is applied before drying. Drying times vary depending on the penetrant removal method and means available to dry the part. Drying can be accomplished using a forced air drying unit or air drying. Regardless of the drying technique, caution must be taken to ensure that the part and entrapped penetrant is not over-dried. For method C, dry times are usually within seconds after the final pass to remove excess penetrant. Solvent-suspended developers in an aerosol should immediately be applied after the test object is dry. Step 5. Indication development dwell. This step also requires a wait time after the part and developer are dry to sufficiently wick the trapped penetrant out of surface discontinuities. Dwell times vary from 10 to 120 minutes depending on the application, penetrant materials, temperature, test object surface condition and geometry, and expected discontinuities type and size. In some instances, discontinuities may appear immediately after the developer is applied and dry, thus the part should be observed as the indications develop. Step 6. Inspection and documentation of indications. Inspection is then performed under appropriate lighting, white light or UVA depending on dye penetrant type, to observe indications from discontinuities. Inspection using fluorescent liquid penetrants requires darkened conditions within a booth or canvas tent for best vision acuity. If discontinuities are visually apparent, the discontinuity may require a measurement and surface marking, as well as documentation by means of photography and/or a hand drawing. Step 7. Post-cleaning. The final step is to thoroughly clean the part surface back to its original surface condition by removing any trace penetrant materials and especially the developer. Developers remaining on the surface tend to wick moisture from the air and can accelerate corrosion on the part. Penetrant dye type. This classification determines what type of dye is mixed in the liquid penetrant. The dyes are specially formulated to fluoresce, visible, or dual mode to increase the visibility of the penetrant and classified by types. Type 1. Fluorescent dye penetrant. Fluorescent liquid penetrant contains fluorescent dye that emits a yellowish-green light fluorescence when exposed to UVA light. The smallest trace amount of fluorescent liquid penetrants left in discontinuities will be clearly visible when exposed to UVA light. Type 2. Visible dye penetrant. Visible dye liquid penetrant contains a dye that is visible under normal or white light. Red dye is most common, although some blue dye is also used. Visible dyes are classified as lower sensitivity than fluorescent dyes at detecting small, tight discontinuities. Type 3 is dual mode, both visible and fluorescent. Dual mode liquid penetrant contains dye materials that are both reddish in color under white light and fluorescent under UV radiation. However, both the intense red visible color and fluorescent properties are reduced compared to the individual visible dye and individual fluorescent liquid penetrants. Sensitivity level. Liquid penetrant systems have variable sensitivities in terms of the ability to detect discontinuities. Sensitivity varies with the type of liquid penetrant and form of developer. Visible and dual mode liquid penetrant types are classified as level 1, low sensitivity, whereas fluorescent penetrant dyes come in any of the 5 following sensitivities: level 1/2, ultra low sensitivity; level 1, low sensitivity; level 2, medium sensitivity; level 3, high sensitivity; and level 4, ultra high sensitivity. The classification term low is kind of a misnomer. Low sensitivity is simply a comparison in terms of the other sensitivity levels, yet it is much higher than visual testing and is acceptable for a large number of applications. The following generalizations can be made about various types of liquid penetrants. Visible dye penetrant is less sensitive than fluorescent dye penetrant. Visible and dual mode penetrants are only qualified to low sensitivity. Removers and emulsifiers. Lipophilic emulsifiers. Lipophilic emulsifiers are composed of liquid blends that combine with oil-based liquid penetrants to form a mixture that can be removed with a water spray. Their mode of action is based primarily on diffusion and solubility into an oil-based liquid penetrant. Parts are generally dipped into tanks of lipophilic emulsifier, withdrawn, and then placed at a drain station for a specified time. The emulsification time varies depending on the viscosity of the emulsifier and the physical action of drain-off. Therefore, it is important to control the emulsification time to prevent over-emulsification of the liquid penetrant in the discontinuity. Hydrophilic emulsifiers. Hydrophilic emulsifiers, often referred to as removers, are composed of emulsifying agents dissolved in water and are supplied in a concentrate form. They are diluted with water at concentrations of 5 to 30% and used as an immersion dip with mild air or mechanical agitation, or as a forced water spray rinse at dilution ratios of up to a maximum of 5%. A pre-rinse with a water spray normally precedes the application of the hydrophilic emulsifiers to reduce liquid penetrant contamination of the emulsifier. The term hydrophilic can be defined as having an affinity for water, whereas lipophilic means having an affinity for oil. Hydrophilic emulsifiers function through a detergent and scraping or scrubbing action. Diffusion does not take place in this mechanism of action. Solvent removers. Solvent removers have traditionally been petroleum-based or chlorinated solvents. However, because the former is flammable and production of the latter ceased in December 1995, the use of detergent cleaners or water-based solvents is rising. Water itself can be used as a solvent for water-washable liquid penetrants. Often a PT emulsifier contains enough solvency to function as a hand wipe remover as well. Developers. Although not a penetrant classification, developers are an integral part of the PT system. The developer's main purpose is to pull the trapped penetrant material out of the discontinuities to be visually observed. In addition, developers create a white contrasting background to further enhance the visibility of discontinuity indications. There are several developer application techniques, including immersion, fog, air, electrostatic, and pressure spray, which are available in various forms. Developers come in 5 different forms. Form A, dry powder. Form B, water soluble. Form C, water suspendable. And Form D and E, non-aqueous. Form A, dry powder. A dry powder applied to dry test surfaces. Dry developer is preferred on rough surfaces and in automatic processing systems. It is also the easiest developer to remove during post-cleaning. Form B, Water-soluble. A developer powder dissolved in water, forming a solution that stays mixed without stirring or agitation. Form C. Water-suspendable. A developer powder whose particles, when mixed with water, are suspended, requiring continuous agitation. Forms D and E. Non-aqueous. A suspension of developer particles in a rapidly drying solvent, normally used with solvent-removable processing. Form D is for use with fluorescent penetrant, and Form E is for use with visible penetrant. Form D and E developers are the most sensitive for the detection of fine discontinuities. As with dry developer, they are applied only to dry test surfaces. Equipment. Liquid penetrant testing can be performed using a variety of equipment types. Typically, liquid penetrant testing equipment is broken down into 4 types. 1. Portable equipment. 2. Stationary testing equipment. 3. Small parts testing units. And 4. Automated testing systems. Portable equipment. Portable PT can be performed on installed parts such as those found on aircraft or on parts too large to be brought to the testing area, such as those found on field welded pipelines or structural welds. Liquid penetrant materials are available in aerosol spray cans and in small containers for brush or wipe applications. Generally, portable liquid penetrant applications are limited to a localized area or spot testing rather than the entire part surface. Stationary testing equipment. The most frequently used equipment is a fixed stationary series or workstations. Each workstation has a specific process role in the PT system. The number of workstations in a PT process line varies, but typically includes immersion tanks for liquid penetrant, remover, or emulsifier, and developer, drain or dwell stations following the immersion tanks, spray wash stations which may be equipped with a UVA lamp, a drying oven, and inspection or viewing booth, which is also equipped with a UVA lamp. Small parts testing unit. Each testing unit is designed for processing uniquely sized parts. The units are sometimes smaller or larger than the general system previously described, and some of the stations serve multiple purposes. In use, the small parts are loaded into wire baskets that are then batch processed through each of the stations. The wash station may contain a water-driven rotary table with spray jets to supplement the handheld spray wand. Automated testing systems. Automated testing systems involve essentially the same process as manual liquid penetrant testing. Automation is used to translate process consistency, reliability, and productivity into quality improvement. High initial costs can be offset by these factor improvements. Interpretation and evaluation of indications. Inspection requires great care and attention. Marginally controlled inspection conditions will degrade the probability of detection of liquid penetrant indications. Knowing and following prescribed inspection parameters will greatly enhance the probability of detecting the smallest discontinuities expected. Preparation for fluorescent penetrants include a darkened inspection area, dark adaptation for the technician, and a UVA light intensity. The darkened inspection area. The darkened inspection area is typically 2 foot candles or less of white light for field inspections and 0.2 foot candles or less of white light for inspection booths. Dark adaptation. Typically 5 minutes will suffice to adjust one's eyes to the darkened conditions to see fluorescent indications. Ultraviolet A light intensity. Ultraviolet A light intensity must be at least 1000 microwatts per square centimeter to ensure the optimal indication of a yellowish-green light fluorescing when exposed to near UVA radiation, with a wavelength of between 320 to 400 nanometers. Preparation of visible penetrants. A well-lit inspection area is required with a minimum of 100 foot candles of white light for visual testing of colored penetrants. Visible penetrants are not as visually apparent as fluorescent penetrants. Additional preparation considerations. The inspection area cleanliness. Stray penetrant on surrounding areas within the inspection area can be distracting and can cause contamination or false indications with test objects. Cleanliness is crucial for indication development. Eye strain. Ensure eyes are not fatigued and vision acuity is not impaired. After spending quite a bit of time under UVA radiation light, your eyes can be fatigued rather quickly, so it's important that if you start to sense eye fatigue, to take a break and let your eyes recover. Observation. This inspection phase requires a visual scan of the test object surface to observe the appearance of any indications. An indication is the visual evidence of penetrant appearing through the developer. Interpretation. This phase requires a closer look at all indications to determine if they are either relevant or non-relevant. Some common relevant indications include continuous linear indications, due to surface cracks, laps, or seams, as we see an example on the lower left corner. Intermediate linear indications due to surface cracks, laps, or seams. However, some of the discontinuity edges are not open to the surface, as portrayed in the middle image. And rounded or dot indications due to porosity or corrosion, as seen on the lower right. Non-relevant indications caused by improper handling may mask relevant indications. Typically, non-relevant indications are faint due to less penetrant bleed out and will not reappear if wiped away and the developer is reapplied. The primary causes for non-relevant indications include improper PT processing during penetrant removal, poor process controls, the liquid penetrant system is neglected, lack of liquid penetrant system cleanliness, and intentional part geometry changes that challenge penetrant removal, such as threads, tight radiuses, or holes. Evaluation. Evaluation is the process to assess relevant indications to determine the cause and type and report their category, location, and approximate size. For a more focused evaluation on some indications, use magnification or the double development technique. The double development technique. This technique provides a more focused evaluation on some indications. Steps include 1. Wiping the indication area with solvent. 2. Allow solvent to evaporate. 3. Lightly spray a layer of non-aqueous developer over the area. 4. Observe reappearance or lack of appearance of the indication. At the conclusion of the evaluation phase of the inspection step, further judgment must be made concerning the disposition of the test object by evaluating it against established acceptance and rejection criteria. NDT procedures specify the acceptance or rejection criteria, as well as supplemental documents such as applicable acceptance-rejection specifications. If liquid penetrant tests are being made on critical parts such as nuclear hardware or jet engine components, an industry expert in indication evaluation may have to be called upon. Process quality control. Frequency of process controls. Liquid penetrant testing is of little use if the materials and/or the equipment are degraded or if procedural deviations exist that reduce the effectiveness of the inspection. To ensure consistent, reliable results, liquid penetrant systems require periodic process control inspections to ensure consistent and irrefutable results. The frequency of process control is established by the Level 3 approved NDT procedures. It is typically set at an interval that correlates with company workload, environmental conditions, and/or industry criticality. Degradation of liquid penetrant materials. PT materials such as the liquid penetrant itself, any cleaners, removers, developers, and so on must be checked when they are brand new to ensure that the product meets expected performance requirements and provides a baseline for periodic inspections thereafter. Once in use, liquid penetrant materials degrade over time for a number of reasons. Contamination of materials is the primary reason liquid penetrant test systems become ineffective. Contaminations include, but are not limited to, water, paints, lubricants, oils, degreasers, dirt, and foreign matter, acids, and alkali cleaners. Most contaminants stem from improper or insufficient cleaning, rinsing, and drying of the test objects. Water contamination may also stem from splashing and overspray in the PT wash tanks. Evaporation losses change the physical and chemical properties of the liquid penetrant materials. Liquid penetrant evaporation increases the viscosity and inhibits or slows penetrant being drawn into discontinuities. Aqueous developer liquid evaporation increases the concentration level, which creates a heavier developer surface coating that could mask small indication. Heat degrades liquid penetrant materials by impacting the physical and chemical properties. Storing materials, immersing hot test objects, or using portable PT materials over 140 degrees Fahrenheit can degrade the fluorescence of materials. Process control of in-use penetrant materials. Process controls are used to validate the entire process to include the materials, procedures, and personnel to maintain inspection consistency. Process control of in-use penetrant. Surface wetting. After applying a small amount of penetrant to aluminum foil, penetrant should not bead up or retract. Rapid brightness test for fluorescent PT. Compare merged drops of reference penetrant and in-use penetrant on a paper towel to evaluate a difference in color brilliance. Water content for fluorescent PT. Use a hollow glass tube to test for water separation from the penetrant. Process control of in-use remover. Remover contamination check. Use a UVA lamp to ensure that the remover is free of floating penetrant that may deposit on the test object. Remover performance check. Check remover performance using 2 oxide blasted panels to compare new reference against in-use materials. Remover concentration check for water content. Ensure remover concentration is correct using a refractometer or hydrometer. Process control for in-use developer, water soluble. Check the concentration of the developer using a hydrometer. Penetrant contamination check. Use a UVA lamp to ensure that the developer is free of floating penetrant that may deposit on the test object. In-use performance tests. Process cracked chrome panels, penetrant system monitor, or starburst panels to check the overall penetrant system quality. Process control of equipment. Liquid penetrant testing equipment requires specific process controls that may need to be conducted before, during, and/or after use. The dryer. Temperature check. Check that temperature and fan attain and hold at prescribed settings. Cleanliness. Check for cleanliness to prevent excess developer buildup and other excessive contaminants. The inspection booth, which is typically inspected prior to use. Your ambient light. Most specifications require the test site to be darkened to 2-foot candles or less when using fluorescent penetrants. The UVA light check. Check the bulb and filter for cleanliness, fit, damage, and required intensity of at least 1,000 microwatts per square centimeter at the test object surface. Cleanliness. Check for cleanliness to prevent penetrant visual noise and clutter which distracts from the inspection. And that concludes this lesson.